Welcome to Unit 2 of GIS for Disaster Risk Reduction, Introduction to Geographic Information Systems, where we'll provide you the core foundations of geographic information systems. This will not make you an expert, as many full courses, certificate, and degree programs exist due to its complexity and power. However, following this unit, we expect you will have a solid understanding of the key elements of GIS, and we'll introduce you to a desktop GIS program and provide some basic comfort for navigation within the interface. The learning objectives for this unit are as follows. We'll discuss the 5 key elements that make up GIS. We'll touch on sources of data, introduce the students to crowdsourcing concepts, describe the difference between open source and proprietary software, and explore some ways in which GIS is employed by organizations. Click on the link below to see a short video that will help convey an understanding of where GIS is going in the coming months and years. The Venn diagram shows how the geography, IT, and disaster risk reduction disciplines interact. To provide a meaningful analysis, all 3 elements must be adequately addressed and respected. It should also be noted that each of these disciplines is in motion, evolving and advancing, and requiring careful thought and continued research. One of the first proper uses of geospatial analysis on record is the famous case of Dr. John Snow, who used a simple map on which he located cholera patients. In this time, it was suspected, but not confirmed, that cholera was a waterborne illness and spurred him to action. In analyzing the distribution of the points, he noticed a clear cluster around the Broad Street water pump. While this might have been sufficient for many, Dr. Snow went further and explored the anomalies, the outliers, and gaps. He discovered that some far away from the pump preferred it and walked there for water. Some nearby thought its water was foul, and being brewers, satisfied their thirst with their own product. Once he was convinced, Dr. Snow removed the handle from the pump to mitigate the cholera epidemic, and the handleless pump stands there to this day. GIS is used by governments in a wide and increasing range of applications, managing inventories of property and buildings, managing natural resources, mitigating disasters, understanding demographics, and many more uses come quickly to mind. Businesses use GIS as well. They use it to identify where they should locate new stores or to identify where they should advertise and how. Delivery companies have been leaders in the use of GIS for route optimization that saves them millions of dollars in gas and vehicle maintenance each year. Citizens use geospatial tools increasingly for many common activities. Navigating is now done with systems in cars or with mobile phone applications. GIS combined with mobile phone and GPS technology allows the citizen to support governments with reports of concerns and help them find anything they need with a simple Google search. GIS is a database system that includes a spatial component and has the power to perform analysis that factors in space to create new and useful information. Successful application of this technology requires the balance of 5 key resources: hardware, software, data, methods, and people. The most important aspect of a successful GIS application is people. Depending on how invested your organization is in GIS, you may need different types of people to ensure your success. If you have a basic GIS functionality, which many organizations have to start with, you'll have a GIS expert who operates the software, a champion within the organization, positioned in a place to advocate successful for the capability. You will have those who provide the resources to ensure sustainability, and a network of technical colleagues in other organizations who can help share skills and best practices. Finally, you'll have customers who desire the analysis and the map products generated by the GIS team, and will provide challenges to the team to encourage their growth and continued relevance. In these groups, the GIS expert compiles the data and makes the map. GIS also requires hardware, some familiar and some highly specialized. Conventional computers and data storage systems are necessary. In the recent past, GIS could only be efficiently run on high-end computers, adding to the cost, but the increased power and improved processing efficiencies of GIS software have made it so that a decent laptop can now power most GIS applications. Specialized GIS hardware includes global positioning system receivers, survey equipment, aerial and satellite imaging systems, and in-situ sensors such as stream gauges and weather stations. We'll dive deeper into this in Unit 3, but geospatial data is unique and ranges from very simple to extremely complex. Common to all of this data is a relationship to some unique information and an unambiguous place on Earth. The three key data structures we'll use are vector, made up of points, lines, areas connected to database records recording details about the feature, raster imagery, which is a pixel-based data structure where the value recorded for the pixel has some meaning, such as reflected color or land use. Finally, we'll look at tabular data. This is simply spreadsheet data that either contains some referencing to a point on the Earth or can be processed or linked to a unique location to become either raster or vector. Where does this data come from? Much of it is provided from official government sources. While mapping technology and now maps are within reach of nearly everyone, historically it's been the domain of governments, largely because of the expense and the need of government to use maps for knowing what they have and are responsible for. Government data is especially important for things like demographics and political boundaries, as this data can rarely be discovered elsewhere. While government data can be considered secondary in nature because they do primary data collection and turn it into finished data or products to share, if you cannot get what you need from the government, you'll need to seek a primary data source. These include conducting field data collection, possibly enhanced with GPS to affix a location to the data you collect. You might also acquire imagery to trace features or process into additional information products like land cover maps. You could use the power of GIS to create new data through the use of models that we'll discuss shortly. Throughout many communities, there are sensors tracking weather, stream flow, traffic, and other dynamic aspects of our community. These are locked in a known location and can be used for making GIS data. Finally, unstructured data with some degree of location information is discoverable in the press and other public sources. With some effort, this information can be brought into GIS for use. GIS software is made up of three key elements which make it unique. First, it has a database that manages the dimension of space. While databases store information on things in highly efficient and retrievable formats, GIS databases also retain the spatial geometry relating to where the feature is and possibly its shape. GIS also has a geoprocessor. This is a data processing engine that can manage the conventional data as well as spatial data. By managing the spatial dimension of the geoprocessor can compare data that has no other aspects in common, and it can also create new information by analyzing a single data type against the dimension of space itself. Finally, it's important that we're able to communicate what we learn from this geoprocessing. This is where the visualization and reporting capability helps out. By providing a canvas to display and style the data into communicative maps, the GIS clearly demonstrates its benefit over conventional databases. The reporting tools ensure that no strength of the conventional database system is left behind, so it can do anything a conventional database can do with maps as an added bonus. GIS software has traditionally been used in a desktop application, but is maturing and gaining more users in server and web-based applications. In some cases, the model you see above is fractured so that this may be three separate systems sharing standard-based data to accomplish the goal of the analyst. These are dynamic times in the GIS software development arena, but the three core elements all must exist in one form or another to be a GIS. Finally, in recent years, many open source tools have come into the marketplace that was once dominated by a few commercial entities. These open source tools are free, increasingly powerful, and very flexible if you have skilled staff and programmers. While they sound like a perfect solution, they're not yet as stable and powerful as some of the commercial offerings, and do not provide the level of support that would come from having a traditionally purchased software license. Each organization must carefully consider which direction makes the most sense, and sometimes it's a combination. Although the GIS is powerful, we know that power without control is useless. Processes and methods provide this control. Processes provide the systematic steps to complete a task with a high degree of efficiency, consistency, and quality. It allows you to improve and refine approaches to production and enhance the capability of your team. Methods are those technical approaches and parameters that ensure you're performing a valid analysis. The GIS will do what you tell it to, but having validated methods designed by subject matter experts You can make sure that what comes out of the geoprocessor is scientifically valid within accepted confidence intervals. One of the ways we manage methods is through the use of models. Models are scripts that retain processing steps and parameters from an established set of inputs to generate new data. They codify the process steps so that each one can be studied and refined and the model improved or itself analyzed if it's not providing the expected results. Thus far in talking about GIS and especially data, we've glossed over one particularly challenging aspect for new students to the discipline: referencing systems and projections. Referencing systems are those coordinates that locate anything on the surface of the Earth. You may be familiar with latitude and longitude, and that's a great starting point, but there are many more. If you were good at Cartesian planes in algebra class, you may not be concerned, but when you consider that the Earth is an irregular sphere and that each system must be built upon a mathematical model of the Earth, that, like the famous saying goes, all models are wrong, but some are useful. For this reason, even to use lat long properly, we also need to know the model of the Earth that we're using. The reference system is typically a concern when you're importing data from field collection efforts or GIS data that's not been projected. Projections are another set of mathematical equations that convert the surface of the Earth's three-dimensional sphere into a two-dimensional visualization or paper map. Projections perform this service at a cost. Based on the method selected, projections require you to trade this dimension from 3 to 2 for some one or more type of distortion, either area measurement, distance measurement, direction, or shape. Now that you're entirely alarmed, I will share the good news. First, the GIS can do all the math. Second, data from professional sources will have reference system and projection information included in the metadata or data about the data. This will allow you to select these parameters from a simple pick list. Finally, the GIS can typically convert these on the fly, meaning you do not have to convert all of your data to one projection. It can handle that for you. Where you may need to know something about projections is when you make a map in the GIS. In doing so, you'll need to know the purpose of the map and make a decision on what you're willing to trade of area, distance, direction, and shape in exchange for a flat map. For example, if you want to make a map for flight planning, you'll want to select a projection that retains direction and distance, but don't need area and shape as much. To keep it fairly simple, I like to think that GIS allows you to do three basic things with spatial information that otherwise would be very difficult: visualize, analyze, and theorize. Visualizing is a powerful cognitive means of communicating. Albert Einstein once famously said, "If I can't see it, I can't understand it." Thus, visualization is critical to ensuring human understanding. This is especially powerful in maps, as they provide a tremendous amount of contextual information based upon concepts of adjacency, proximity, and co-location. These elements are critical in disaster risk reduction applications, as areas adjacent to a hazard may be ideal for evacuation routes. Proximity to a hazard may warrant education of the community, and co-location with a potential hazard warrants some mitigation considerations. GIS can also analyze, taking existing information and turning it into new information. For example, landslide susceptibility maps are made by taking elevation, soil, geology, and land cover maps, and finding locations where each of those characteristics are conducive to landslides. 4 data layers come together through the geoprocessor to make one new layer. One of the most powerful aspects for DRR is the power to theorize. GIS can explore a range of future conditions before they occur and provide some understanding of what could be expected from those events. This is frequently used in land use planning, as cities want to understand the impacts of development on everything from traffic to shadows and sightlines. In DRR, you'll learn we can gain an understanding of what a hazard event might do to our community if it occurs. We can run a range of scenarios and even modify the community in the GIS to see if changing something might lessen the impact. Let's look at a few examples. This map from the 2014 Ebola outbreak in West Africa provides the reader a quick understanding of the extent and severity of the outbreak and the response activities ongoing. It also provides, at no extra charge, an understanding of the other adjacent countries who may be at risk or may be safe areas for staging responders. As described previously, here's a graphical representation of a model showing the many steps in an analytical process, and the map to the right shows how the data created from such a model might appear. This slide, borrowed from my colleague Dr. Faraz Raji, is a great listing of analysis types that can be applied to humanitarian operations. This graphic shows the ability of GIS to theorize. In this case, what if the great 1906 earthquake in San Francisco happened on today's city? This model contains a hazard modeling tool, community asset database, building code information, and additional models to estimate secondary and economic impacts. Click on the graphic to see a slightly dated but informative video on the hazards model. In summary, we need to understand the big 5 elements of GIS and make sure all are addressed in our planning and implementation. GIS is a powerful tool, and with that power comes complexity. Carefully consider the costs and benefits of any scale of investment in GIS. Recall the 3 key elements of the GIS software: the geo-enabled database, the geoprocessor, and the visualization platform. Referencing systems and projections are important technical considerations that, though enormously complex within the GIS, are easily managed through the interface. GIS allows the user to visualize, analyze, and theorize in 3-dimensional space, creating a powerful tool for management and planning. On course sites, navigate to the Lab 1 folder and complete the exercise described in the document provided there. Thank you for completing this unit, and be sure to take the short quiz on course sites before starting the next unit.